We are recording. I hand it over to you, Giandomenico.
Giandomenico, maybe you're muted.
Sorry. I say again.
Yeah, start again, Giandomenico. Okay.
It's a pleasure to have today Miguel Montero from Harvard. So he's a postdoc in the Cobartism group, and today he's going to talk about the Swampland and the string universality. So please.
Okay, well, thanks a lot first of all, to Daniel for the invitation, and Giandomenico for the invitation, for the nice introduction, and to all of you for being here and to listen for this opportunity to present my work. So I'm working on sort of, you could even call it, I think by now it's fair to call it a subfield of quantum gravity research that basically exploded over the last 5 years, which is called the Swampland. So I'm going to start with an introduction to what the Swampland is, and then I'm going to show you how to use the techniques in the Swampland to achieve what in the string and supergravity literature would be considered a powerful result, the idea that I'm going to use it to show that in certain cases, in high dimensions and with a lot of supersymmetry, so those are caveats, the only consistent quantum theory of gravity is string theory, okay? So that's what I call string universality, okay? So let me start, but before I do that, there's a very important thing that I need to do, which is to, well, I think then you already told me that you guys like to ask questions. That's precisely what I want, okay? So I need interruptions, I need feedback to see if the message is getting across, so please ask whatever you want anytime, just interrupt me, okay? Good, so let's get started. So as I said, I'm interested in understanding quantum gravity. And I want to understand quantum effects of gravity, as I guess all of us do at some point. And so this is difficult, as you know, because, well, this is the Einstein-Hilbert Lagrangian that's describing the classical piece of gravity. And the coupling in front of it is a dimensionful coupling, has M Planck. And that means that if you want to get to the regime where the effects of gravity are strong, to get to strong coupling, you need to reach energy scales comparable to the coupling. That's 10 to the 19 GeV. And I don't think that's going to happen anytime soon, to put it mildly. So if you want to understand quantum gravity, you need to do something else. What can you do? Well, there's a very fruitful line of research that you could pursue, which is to focus on.
I think you've 1 over m squared. This is the Planck length, probably. I mean there.
Sorry, what?
It's m Planck squared. It's m to the +2.
So it's m Planck squared, yes.
Am I doing it wrong? You need a mass squared there in front of it, rather than an inverse mass squared. Relevant operator rather than an irrelevant.
Oh, you're completely right. Yeah. Sorry. Yes, it's 1 over 8 pi g, which is the same as m Planck squared on top. That's right. Thank you. Good. So what can you do? Because this is kind of hopeless. Well, one thing you can do, you can focus on theoretical problems. They're very, you can focus on theoretical problems of quantum gravity that you can analyze just from the theoretical point of view, like black hole evaporation, and trying to understand what kind of features has a unitary process of black hole evaporation have. And you can make a lot of progress down the road. Another arena where you might think you can make some progress is that, okay, maybe if I look at the area of the universe and inflation and such, then the high energies during inflation, the inflationary scale is maybe 3 orders of magnitude below the Planck scale. So maybe you get a chance of seeing some small effects there. It's also promising. But in any case, it seems that there's no way that you're going to be able to say anything interesting related to gravity in a universal way, about the deep IR, about properties, of the low energy effective field theory. Okay. Well, as I told you, I'm working on this subfield, which is called the Swampland, which is entirely based on the observation that there are certain universal principles that are hinting very strongly at the idea that this point is just wrong. You can say interesting things interesting things from the point of view of particle physics, interesting things about the low energy effective field theory, okay? So now I wrote down bigger Lagrangian with still the wrong power of n Planck, but now I introduced a Lagrangian for a quantum field theory that is describing matter. So in the real world, that's the standard model. That's just the matter fields that couple to gravity and so on. Okay. So that's just the Lagrangian of the effective field theory. And it's just from the point of view of just bottom-up model building, this can be anything. Just pick any quantum field theory you want, take its Lagrangian, put the square root of minus g in front of it, and you can couple to gravity. So, I could draw a blue blob, which is the space of all quantum field theories. And as far as, low energy considerations are concerned, it looks like you can pick any point in this blue blob, write down the corresponding low energy Lagrangian, and say, well, that looks like matter coupled to gravity. And anything can go, in principle. The Swampland is based on the idea that this is in fact not true. And a more accurate picture is that inside this big blue blob, there is a green blob, a subset, a proper subset of theories that can actually arise as the low energy limit of Einstein's gravity coupled to matter. Now, we call theories in the green blob, we say they're in the landscape, which is language that comes from the string theory landscape. String theory is maybe not the right quantum theory of gravity in the real world, I don't know, but it's certainly a consistent quantum theory of gravity, which produces many solutions, which leads to millions of effective field theories that you can consistently couple to gravity by construction. And that set of solutions is called the string landscape. So by extension, we say that any effective field theory which is okay with quantum gravity is in the string landscape. And there's also a bunch of theories. In fact, the majority of quantum field theories that are not in the landscape. And so we say they're in the string swampland. Is there any question? Okay,
Not
good.
at the moment, I think you're okay.
Yeah, it's just when I hear something, I will stop, ask for a question. If there's nothing, I will just continue in a second. Okay, so that's the landscape, that's the swampland. And the goal of the Swampland program is to tell you which effective field theories are in the landscape and which ones are in the swamp. Okay. Now I'm not going to do that. We are not doing that, but trying to write a list of theories. That would be stupid. We are instead trying to come up with general properties that theories of gravity that are in the landscape must satisfy, as opposed to theories that are in the swampland. Okay. So we're trying to give universal constraints. Now, if this is true, this is big news, because that means you get constraints on the matter sector. Maybe you can explain some properties about the standard model Lagrangian. Why does it look like it the way it does? You can combine with one of the previous approaches that I mentioned, inflation. If you combine Swampland ideas with inflation, they get pretty powerful, and you can actually make there's a real hope of getting precise statements about observables in cosmology, like the tensor to scalar ratio. And one problem which certainly involves both gravity and particle physics is the hierarchy problem. You might hope, and in fact this proposes that you can learn something about that as well. Okay, so that's in a nutshell what the Swampland program is, what we want to do, and why we're excited about it. But really, the question one should be asking is, okay, fine, but why? What is the evidence for all this? Why do you think that any of this is true, that you can do this bizarre thing? Well, there's basically two lines of arguments supporting all the claims in the Swampland. Some of the claims in the Swampland are supported by very general arguments coming from precisely the studies of unitarity of black hole evaporation. Whatever your quantum theory of gravity is, it better produce unitary black hole evaporation. And so we are confident that anything that we can argue based solely on that principle is going to hold generally. But then, if you have a general argument, it's always good to double check with examples. And the example that we have, for instance, is the examples that we have lots of empirical evidence, so to say, I put it within quotes, coming from string theory, meaning that once we have one of these black hole arguments, we think it's true, we go and check in string compactification after string compactification, we see that it's true. Okay? Question so far? Okay. So fine, I gave you why, I give you evidence. I give you the reasons why I think there's evidence for these things. But can you prove any of these claims? Can you really rigorously prove them like the way we like to do in quantum field theory? Well, the answer is that sometimes I can, but only in restricted contexts that do not cover all the examples. And the reason for this is that unlike quantum field theory or quantum mechanics, we just don't have a framework which allows us to prove things in general in quantum gravity. For instance, but there's one, I said above that sometimes you can prove these things in restricted contexts that don't cover all the examples. And that happens, for instance, when you have quantum gravity with a negative cosmological constant. Okay, that's quantum gravity in ADS space, because then you have the ADS CFT correspondence. And you can translate complicated statements about quantum gravity in ADS to non-perturbative statements about the dual CFT. So the situation there is better, and you can actually prove some of these claims. But I care about quantum gravity in general, not just in anti-de Sitter space. In particular, the real world is certainly not anti-de Sitter. So if you ask me, can I prove these things in general? The answer is no. So the best that we can do is we organize our knowledge in a web of interconnected conjectures. So there's a bunch of statements that have different degrees of support and validity, but which are all related to each other. You can often derive one from another or show that at least they are consistent in certain regimes. And the fact that all the statements are consistent with each other gives credence and makes us think that the whole picture is trustworthy. So I just drew here some of the more popular Swampland conjectures. I'm of course not going to be talking about most of them, but maybe you have heard about the unitarity conjecture. That's one which is particularly famous. So people who work on the Swampland, such as myself, we do two kinds of things. First, we prove these conjectures in setups where we have control to prove them, and they haven't been proven yet. We also check them when we cannot prove them. And on the other hand, we apply these conjectures to interesting models of particle physics and phenomenology, and also use the general principles when we think we understand them to propose new conjectures. Okay, so I've worked on both these things, and today, instead of giving a more general overview of the Swampland, I'm going to focus on two of the Swampland statements that are the two of them that are one of them is the most established Swampland statement, the one big idea from which we believe all of Swampland ideas hail from, and then the second one is basically a consequence of the first, which I think it's particularly nice to talk about to an audience with expertise in condensed matter physics, because it's telling you that gravity is very much like a condensed matter system in the sense that condensed matter systems have boundaries, and the second conjecture tells you that quantum gravity must have boundaries as well, in a sense that I will describe shortly. So now I'm going to be talking about the first conjecture, the absence of global symmetries in quantum gravity. I'm going to make a small pause for questions. Okay. So I'm saying that there are no global symmetries in quantum gravity. What does that mean? Well, to tell you that what does it mean that there's no global symmetry in quantum gravity? I need to tell you what a symmetry or is, right? Or a conserved charge. And of course, at its most basic level, a symmetry is just a charge that is conserved by a dynamical process. So for instance, I drew here a process which is a valid one in the standard model is Neutron Decay, right? And this is a process that has that has several quantum numbers that are conserved. So for instance, electric charge is of course conserved. Standard model also has this another conserved quantity, which is baryon minus lepton Lambert, which is its precise definition is not really important now. All it matters that it's conserved in all processes by the standard model. So this one has one to the left, and of course has one to the right. Now, that's what a symmetry is. Both the things above are symmetries. But more generally, symmetries can be you can classify symmetries into two kinds. There's what I call a long-range gauge symmetry. It's a symmetry where the conserved charge can be measured from far away. Okay. in particular, the electric charge is an example of a gauge charge, because you can measure electric charge from far away from a system just by integrating the electric field, just for Gauss's law, right? That you don't need you don't need to go in, get close to the neutron and proton and count them or whatever. You just know that the electric charge is zero from far away. There's examples of also discrete gauge symmetries where you can measure discrete charges from far away. And in that case, you need to use more like a Aharonov bomb kind of effects rather than just measuring field strengths. But the basic hallmark of a gauge symmetry is that you can measure it from far away using some sort of holonomic. By contrast, a global symmetry is the rest of the symmetries. Symmetries whose global charge, whose charge cannot be measured like this. For instance, in the standard model, this B minus L thing, it's not coupled to a gauge field that we know of. So if you want to measure the change in B minus L reaction, you really have to count how many particles went in, how many particles went out, and count their numbers. Okay, you actually gotta get close to the actual process. So that's the difference. And now that I introduced the difference between these two things, the conjecture is pretty simple. The second thing can never happen when coupled to quantum gravity. Okay. So that's an example of a Swampland statement. It's telling you that not every low energy effective field theory you can couple can actually, you can write down, can actually be coupled to gravity, because if it has a global symmetry, well, then it can. And in fact, just to tell you, to illustrate again why we're excited about this kind of thing, this has real world consequences. This one in particular, because B minus L, as I told you, is a global symmetry in the standard model. And so if the essence of global symmetry conjecture is true, it means that it's either coupled to a yet unseen fifth force. So there's a massless gauge field that couples to B minus L. It has to be extremely weakly coupled to comply with experimental constraints, but that's one possibility. Or it's not a real symmetry. There's some process in the standard model which we haven't seen yet. There's some process in the theory which haven't seen yet, such that the symmetry is broken. And examples of, yeah, is there a question? Okay, so examples of such processes are things like double beta decay or proton decay. People are looking for this. Okay, so applying just this very general thing leads to interesting constraints on low energy physics. On the other hand, these constraints are not that interesting because it tells you something. This is telling you that, yeah, this thing has to be either broken or gauged, but it doesn't really tell you anything quantitative, because I didn't tell you, this argument doesn't tell you how weakly gauged it has to be, how small the gauge coupling has to be, or if it's broken, how badly it must be broken. And if you're gonna say that B minus L is broken by a process that happens, basically never happens, it's so suppressed that it basically never happens, then even though technically this is a constraint on low energies, it's not a very interesting constraint. Okay, so what I'm gonna be showing you in this talk is how this principle, when you combine with other ingredients, in my case it will be supersymmetry, which I guess it's a bit of a put off, but I'll coming back to that later. When you combine it with supersymmetry, it actually becomes very strong, and it can produce very non-trivial constraints on the deep IR of the theory. Okay, so of course the hope is that we're using supersymmetry now as a crutch, and then we're going to be able to remove the crutch. But baby steps. Okay, so this is the conjecture. There's no global symmetries in gravity. But why do we believe such a thing is true? Well, on one hand, this is supported. Originally, this is supported by arguments about black hole decay or absence of remnants. Basically, there are old arguments from the 80s and 90s that say that if you start with a black hole and there's a global symmetry in your theory, you can throw global charge into the black hole. Hawking radiation is insensitive to this charge. And so when the black hole evaporates, you end up with a remnant which is stable by kinematics and has all the global charge. And therefore, you could have arbitrarily many states in an arbitrarily small volume of space. This violates the second law of thermodynamics when you take into account black holes in the form of Bekenstein's bound. So there's arguments like that. Then of course, there's also proof of it in perturbative string theory. And string theory is really easy to prove. It's just, this is not a general argument. That's the first one, but it's some evidence. And as I told you, often you can prove these things quite rigorously in the context of holography. And in the context of holography, this one in particular is really beautiful. It can be shown to be equivalent to Noether's theorem in the dual CFT. Okay, so it's related to something that we all know and are familiar with. And well, there has been a recent understanding. This one is actually related. The arguments using entanglement West reconstruction are related to black hole arguments. So there has been a very recent understanding over the course of the last 2 years about how to finally describe a unitary black hole operation process for which you need to reproduce something called the Bayes curve. And we know how to do that. And by summing over certain saddles in an Euclidean path integral. Those saddles that you need to introduce to reproduce the correct Bayes curve are also also introduce effects that break global symmetries, and this has been established in recent papers. Okay. Finally, I said it's true in perturbative string theory. What about non-perturbative string theory? Well, in non-perturbative string theory, which we can sometimes analyze, we don't have a proof, but again, it's true in literally every example that we know, and we know a lot of them. Okay, so this is basically what I have to say about this first conjecture, which is at the core of the Swampland program. Any questions about any of this?
Okay, I have a question. So,
please.
I remember that Gaiotto and Seiberg, they have this higher global symmetry. Are you saying that also these are completely absent?
Yes. Thanks, Domenico. That's a great question. Indeed, it's very important. Actually, yes, indeed. So basically, when you have a higher form global symmetry, so the global symmetries are described as particles that are the charged objects, right? But you can also have symmetries under which the charged objects have higher dimension. You can have strings, membranes, and if you like string theory and like working in 10 dimensions, you can have also D3 branes, D4 branes, all the other branes. They can also be charged under these things. The arguments that I was describing here, they all of the one about this last one has only been done for what I call zero form global symmetries, right? So those ones only work in flat space. All the others apply also to generalized global symmetries. Okay.
Presumably, your statement is not restricted to 4-dimensional quantum gravity.
Indeed.
So, because you're basing it on black hole physics. So, can you not make the statement more quantitative in lower dimensions? For instance, in 2-dimensional.
Oh, I see. Well, right. So here's the thing. Very good question. Right. If you try to make these arguments in let's say 3 or 2 dimensions, you find a problem. Well, the problem is with the problem is that only in 4 dimensions and more you have dynamical gravitons. Only in 4 dimensions and more you have black holes as finite energy excitations of empty space that can evaporate back to empty space. For instance, in 3 dimensions, let's say you're doing 3 dimensions. This was originally studied by Toft. In flat space, there's no black hole solutions, so there's no way for me to make the argument. And if I go to ADS, you can have what people call BTC black holes. They are large black holes in ADS, but they're in equilibrium with their own radiation. By construction, they don't evaporate, so you cannot make this argument. Also, the ADS-CFT correspondence in the case of ADS3-CFT2 is slightly different. So the connection between global symmetries in one side and another theorem in the other is not as clean. And if you go to 2 dimensions, basically the same arguments happen. There's basically no dynamical graviton. You can have of course, you can have theories with a metric, and you can make the metric fluctuate at the quantum level. But the fact that there are no dynamical spin to excitations makes the thing very different.
Sorry, Miguel. So in 3D, there exists also massive gravity. So where you can really give basically dynamics to the graviton by, of course, modifying the Einstein-Hilbert theory. with the Chern-Simons term. Maybe in that constant, you know, that
Good.
case, maybe something.
Good question. I haven't thought about this one, so I don't know. But yeah, so with massive, you're saying that when you give a mass, you can make the graviton dynamical. I see.
Yeah. But then you break time-Hertz symmetry, so you are breaking some, you know, fundamental symmetries like.
Yes. Yes, of course. Of course, I didn't say, but behind the scenes in all of this, I'm assuming Lorentz invariance. There's a very interesting question which hasn't been explored. How much of this and to what extent is true in theories which spontaneously break or explicitly break Lorentz, like or Java gravity, or I understand what you're saying.
Yeah, also some discrete part of Lorentz, not the whole Lorentz group. Just you know,
oh, sorry. You're talking about parity. You're breaking parity.
Yeah,
no,
this, parity. Just
no. Sorry. This all applies also. So breaking parity is fine. I was talking about the connected part of Lorentz. Sorry, I misunderstood you. Then I go back to my previous answer, which is I don't know. I haven't thought about massive gravity in 3 dimensions. Okay, good. So that's no global symmetries. And now I'm gonna switch to the other conjecture, the one I'm actually gonna be using in the second part of the talk, which is the so-called Cobartism Conjecture by McNamara and Baffa. And I think so. For instance, as I said, I really like talking about this one. You know, this is a quantum gravity conjecture, which is easier to convey and to describe with people with expertise in condensed matter than it is to string theorists. What the Cobartism conjecture tells you is that any consistent quantum theory of gravity must admit a boundary condition. What do you mean by a boundary condition? I mean that space-time ends. So what does it mean that space-time ends? I mean that there's a space-time, there's the end of space-time, and you just basically hit a wall and you cannot proceed any further. And you cannot proceed any further because on the other side of the wall, there's nothing. There's not even space-time. You could say that the graviton has been gapped. It's a gapped phase of gravity, and so there's no geometry. Okay, that's what the conjecture tells you. And in fact, as I said, it's easy to describe to a condensed matter physicist because it's telling you that gravity really behaves like a lattice system. If you have a lattice system, well, literally every lattice system that we can have in the lab has an end at the end of the lab, right? So this is the same thing, only that now space-time itself that is being gapped. Okay, so in fact, let me emphasize something very interesting. There's a lot of the evidence that we're accruing from the Swampland program points to the idea that gravity really is described or can be described at the fundamental system, at the fundamental level, like a lattice system, which is an area which is prevalent in other approaches to quantum gravity. So why do I say this? Well, lattice, I told you that you don't have global symmetries, and Giandomenico introduced these generalized global symmetries. Lattice systems also don't have generalized global symmetries because they involve, you know, extended objects. The charged objects in our generalized global symmetry are things like strings, but in lattice systems like this, I can always break a string here or there. So they're not charged into that. They cannot have generalized global symmetries. And they also admit a boundary. So it's pretty much like a lattice system, which I find really appealing.
You're talking about spatial boundaries rather than a time-like boundary.
Correct. I was talking about space-like boundaries. Yes, this is a space-like boundary. Yes.
So what is the topology of this space-time then, if you take 4 dimensions?
If you take 4 dimensions, what do you mean? What's the topology? Well, right. So you can actually, we believe that quantum gravity should make sense. There's dynamical topology change in gravity. Usually we say that gravity makes sense on any topology. But in this particular example I was describing, the topology is just half R4. Let's say we have gravity in 4 dimensions, and we just say that there's a boundary to the theory at x = 0. That's it.
And so what is the mass of the graviton if it's gapped?
Well, yeah, so that I meant more as a poetic description. So I don't what I mean, right. So what I mean is that in Einstein's theory, you have a metric, and intrinsically associated to the metric description, you have a massless graviton. Because I don't have the metric on the other side of the domain wall, then the graviton itself must have been, you could say that the graviton itself is gapped, and I don't know what the gap is. I'm not even sure. It's actually, it's not very precise, because this being gravity, you don't have space, but you also don't have time. So what is the Hamiltonian? I don't really know. Really, the statement that I'm making is that gravity makes sense of spaces with boundaries.
Okay.
Just to clarify, I mean, you can have a topology there. The metric can be absent, but you can have a space-time there.
That is true in general.
So is that
no? You're saying, for instance, when I have a topological quantum field theory, right? I don't have a metric, but still have.
But it could be a topological quantum field theory at the other side of.
Very good, very good. Yes, you're right. It could be, and I think that that's a possibility. We just don't know what the answer is. But everything I'm gonna say in this talk is gonna be independent of what happens on the other side. I just know that space-time ends there. You cannot go after that, and maybe there's a smart way to describe this as a gaps. TQFT, where sure there's no metric, but still there's some notion of topology that matters for the partition function when you complete that.
I mean, as Denjo asked you, I mean, space-time does not end there if time doesn't end there. It's only space that ends there, right?
Yes, sure. I'm just
Well, it's not a compact space-time, and also
no, it's not a compact space-time. That's right. So time extends. That's true.
Yeah.
And what I'm saying is that on the other side, I'm being completely agnostic of what's on the other side.
yeah, well, you can be as agnostic as you like, but then if you have a finite spatial region and something like a block in R4, you have to have a boundary condition then when you solve equations.
Of course. Very good. That's indeed, that's very important, and that's what makes this quite difficult and non-trivial to satisfy in gravity.
What's the natural boundary condition?
So what's the natural boundary condition?
Yeah.
So that's, for instance, Dirichlet boundary conditions for the graviton that's reflecting. And actually, it gets more interesting because sometimes there are some quantum theories of gravity that we have in string theory where the bulk theory is chiral. Okay, so you have chiral modes in the bulk. Well, let me be more precise. You have certain fields that have chirality, and so it seems like that would be going to be an obstruction to put the theory in a boundary. But the precise spectrum of fields that we have is such that when you take all the fields together, they admit a boundary condition because anomalies cancel in the bulk, and this is very non-trivial, and it happens in every example.
Can I ask? This is less than what, for example, Raphael Sorkin and others attempt, where the topology of the spacetime itself is emergent from quantum gravity. Here, that the topology is supposed to be given, but then where does it come from? I mean,
yes, very good. Wow, this is an excellent question I was not expecting. So the point is that, right, you're completely right. When you're doing fully non-perturbative quantum gravity, the metric topology, everything is emergent. You're supposed, at best, we don't really know how to do that on a compact space. You're supposed to, at best. For instance, if you have some asymptotic boundary where gravity is weak, then you're supposed to dynamically sum over topologies, boundaries, and whatever you have inside, right? That is true. But the point of view that I'm taking is that in weakly coupled theories of gravity, which are Einstein plus matter, you can take you must sum over all these topologies, but at the level of the effective field theory, you can treat the geometry and the topology as background fields for the effective field theory. Okay. And then for the whole picture to make sense, it better be that the effective field theory itself makes sense on every background you're going to be summing after when you do the gravitational pathing.
The existence of manifolds with boundaries for quantum field theories, that is not a surprise. It happens, for example, for QCD. Okay, you can take QCD in a S3 also, disk cross R, and you can formulate it in terms of boundary conditions you get. So why is this surprising? Well, you can put boundaries, but
good. Maybe it's not surprising to you. Okay, so here's my understanding. The reason why this is often true for quantum field theory is because quantum field theory often, not always, but often admits a lattice regularization, and so the argument that I drew here applies. So I agree with you; it's not surprising for quantum field theory. It is certainly not always true for quantum field theory. If you have a quantum field theory, and this was proven recently, I think. If you have, well, the versions of the statement are old, but it was proven in general recently. If you have a quantum field theory that has a global symmetry, and there's an anomaly under that symmetry, then there's no boundary condition which preserves the symmetry for that global symmetry. Okay, so sometimes you cannot, in fact, put some quantum field theories in spaces with boundary. Of course, why is this never an obstruction in gravity? Well, because I told you, gravity has no global symmetries.
Again, I'm bothered by this. Normally, in people approaching this kind of problem, there is this Galvanized theorem, which says that if you give me the algebra of observables, which is C-star algebra, you can recover space-time from the algebra in terms of the spectrum of the algebra. And there is elaboration of this by Kohn and others. And this is what is proposed in local quantum field theory, where you have a net of these phenomenal algebras, and there are attempts to recover space-time from that. But what is being attempted here is much less, okay, from what I see. Okay?
Yes, indeed. This is, yeah. So first of all, the approach in axiomatic quantum field theory is really good, and all these things related to like construction of space-time, out of operator algebras, and the Ritz-Leader theorem, right, and all this stuff is very quantum field theoretic, right? It's not clear by any means that this applies. It can certainly be used to reconstruct to some extent the background space-time from a quantum field theory, but it certainly, I don't expect that it applies, when gravity is dynamical. But you're right, we're being less ambitious here. We are being significantly less ambitious here. We are just saying, look, my quantum gravity is gonna have to make sense in space with boundary. This is in fact true in string examples, right? So that's why that's where we have a lot of examples. Where all these phenomena that I was describing, where things look chiral, but in the end you can actually give them a consistent boundary condition. And I agree with you, it's less ambitious. But you will see, I hope, that even though it's less ambitious, it can still tell you very interesting things.
Again, I'm not very. So, is this space-time you are assuming globally hyperbolic, and you are assuming that you are given a hyperbolic operator in the space-time? So, like box of in a background metric, for which you are finding self-adjoint extensions and so on, or what? I mean, if you say boundary conditions, you must have some operator, okay? Some operator which is acting in the space-time you are looking at. What is that operator? What is that operator? Is it globally hyperbolic, this space-time?
The example that I wrote here, yes. It's so let's say half of Rn is certainly a globally hyperbolic space-time. So okay, so to be globally hyperbolic, as you're pointing out, you need to specify boundary conditions for the fields of the boundary. So for some fields like the graviton, that's easy. You can just specify Dirichlet boundary conditions, reflective boundary conditions, and that's totally fine. For some other fields, like the chiral fields that often arise in string theory, you need to specify more complicated boundary conditions. What I'm telling you is that it can always be done. So I'm just having some lower effective field theory, some Lagrangian, the one I was describing before, which has some quantum fields, and I'm imposing things like Dirichlet boundary conditions at the boundary. Okay. Importantly, in some examples, when it's not possible to do this by itself, you will have also edge modes. And this is a very important part of my story. Sometimes you will also need to introduce the appropriate edge modes, which are degrees of freedom localized just at the boundary. And the boundary condition for the whole system involves coupling the bulk modes to the edge modes. Does that make sense?
In quantum Hall effect, okay, where you have edge modes, and that cancels the anomaly coming from the Chern-Simons term. So
it's going to be very much like that.
Okay.
And can you take a limit where the blocked R4 goes to infinity? I mean, you have an infinite volume already because it's infinite in one direction, but can you push the other one to infinity, or?
Yes, well, yeah, the way I'm thinking about it, that's what I'm doing. But yeah, certainly you could imagine doing it, that's what I'm imagining, but you could also do the other thing, like you put it on a box if you want, right?
Well, yeah, but what happens then? Does the theory become trivial? Because if you're relying a lot on some boundary effects, you'll have to control that, and it might tend to something that you don't like. No? So
right. So here's the thing. The theory that I'm talking about has dynamical degrees of freedom in the bulk. It also has a certain topological sector in the bulk which induces edge modes, but they're, so the theory is even trivial if I put it in a box. Okay. But yeah.
Okay, right.
Hi, I just had a question. You said that the space-time was globally hyperbolic in the example you were considering?
Yeah, that's right. Well, for me to say that, that means that I have a consistent initial value problem, right? And of course, I need to specify boundary conditions for this guy at the edge. So that's a very important piece of me saying, strictly speaking, globally hyperbolic is not the notion that I need. What I need is that the initial value problem is well posed, and because I have boundaries, I need to study boundary conditions with the boundaries.
Okay, I was wondering because often in string theory, the case is that you're looking at this background topology that's changing. You know, if you have a string interaction.
Oh yes, good. Well, yeah, that's on the worship, not directly on spacetime, but it's also true that topology can change dynamically in spacetime in string theory. But again, the perspective, that's kind of like an perturbative, strongly coupled process. And I'm talking about what happens to the effective field theory on a fixed background. Okay, so I'm taking I'm talking not just about any gravity. I'm talking about only weakly coupled gravity, where all these things make very good approximate sense.
Right. Yeah. I just want to make the point that if you do have the spatial topology changing and you are talking actually about spacetimes, then your spacetime is definitely not globally hyperbolic.
Totally agree. I don't know what happens there. Yeah.
There isn't really a well posed boundary problem for a spacetime where the topology changes currently, anyway.
Yes, I completely agree. I think. What are your thoughts on this? I think that certainly the only way that I know how to make sense of fully non-perturbative quantum gravity in any sense is via holography, where I by hand say, you know, far away gravity is going to be weak, and then in the bulk I allow it to do whatever.
I think your notion of quantum gravity would be quite different from mine. I imagine you're often thinking of things in a Euclidean context, where you formulate those sort of ideas. Coming from the space-timey context, things would be quite different.
Right, I completely agree. Yeah, so what I'm computing is more like correlators or matrix elements of things which are far away. Maybe in Lorentzian signature, but certainly all of this can be continued to create. Yeah, okay. Yeah, thanks a lot for all the questions. Are there any more? Good. So I was telling you, why do we believe this thing is true? Well, part of the evidence is true in string examples, and as a matter of fact, as it was shown in this paper, it is related to the absence of generalized global symmetries that Gian Domenico was talking about. Okay, so I can talk about that if you want me to. It's not the main point of my talk. So unless people ask me to talk about this, I'll move on.
No, talk about the main point.
Yes, when everyone says something like this in a talk, you're pleased, of course. Good, right. So what is the relation between breaking generalized global symmetries and putting theories on boundaries, right? Well, the point is that you can often relate the two via compactification. Okay, so let's say, for instance, you have a 4-dimensional theory of gravity. Let's say that the Lorentz effective field theory is Maxwell's theory, and such a theory has by itself a one-form global symmetry, under which the objects that are charged are simply flux tubes of magnetic field, like tiny magnets. These things cannot break because of Maxwell's equations, because breaking them would require monopoles, right? So that theory has a one-form global symmetry. And related to that, you can do what in string theory we call a flux compactification, which is to consider the theory in a different background, which instead of R4 is R2 times S2. So plane times a sphere, and the sphere is threaded by magnetic flux. Okay, so that's so you know, from this parent 4-dimensional quantum gravity, we got a 2-dimensional quantum gravity with flux under the S2. Now, if you say that the parent theory, that this one-form global symmetry under which the fluxes are charged is broken, that means that you're adding monopoles that allow the flux tubes to break. And if you add the monopoles that allow the flux tubes to break, you also, the same monopole can constitute a boundary mode for the compactification I was describing. So there's a one-to-one correspondence between these two things in this case. And what these guys do in this paper is to establish that more generally, quite generally. All good? Okay, good. So, fine. So now we're coming to the central idea of the talk. The central idea of the talk is that this Cobartism conjecture becomes, that you can put gravity in a boundary, becomes very powerful. And the ideas that we're getting are just gotten from things like the topological superconductor. Is not high-end technology. It's just has never been applied to gravity before. And so the point is that if you remember, the whole point of what I want to do is to get constraints on low energy physics, and applying directly this no global symmetries principle results in constraints which are boring and weak. But in the form of the Cobartism conjecture, something interesting can happen, which is related to the fact that indeed, for some theories, it sometimes happens that the boundary has chiral H modes, like a topological superconductor. Okay. So very much like a topological superconductor, but with one.
One question before you go on.
Please.
Why is it called the Cobartism conjecture?
Great.
Because I didn't see a Cobartism means I have two boundaries.
Excellent. Yes. So it's yeah. So I just gave you like a concrete consequence of the statement. The actual statement that people are making is that it's not just that quantum gravity admits a boundary, is that there is a dynamical domain wall between any two possible quantum gravities. Again, this is not surprising in point of view of a lattice description, quantum field theory, right? Because you just have two different materials and you can glue them with with some interaction Hamiltonian in between. But from the point of view of gravity, it's not trivial. So the idea is that everything can be connected to everything else by a dynamical transition. And if you're discussing this in the context of string compactifications often have an internal space, which is some Calabi-Yau manifold with complicated topology. And what this is telling you is that you can transmute one Calabi-Yau into another, and the way you do it is via, in this particular case, is via cobordism. So two Calabi-Yaus are cobordant always, for instance, in the mathematical sense of cobordism. Should I explain mathematical?
Okay, no, that's fine. I understand what you mean now. Yeah, thanks.
Well, as I was telling you, this is very much like a topological superconductor, which is great because we can use all the condensed matter literature. But there's one important difference, very important difference with the topological superconductor, which is as well, it has chiral modes as topological superconductor, but the Ward volume spectrum has to satisfy other constraints. Okay, so for instance, it has to be supersymmetric, and it has to be supersymmetry, also unitarity, and consistency of Dirac charge quantization. And all these things can constrain the boundary modes independently of this other thing. So you have two different principles. They are both constraining the boundary theory, and sometimes they are actually incompatible with each other. Sometimes you can show that anomaly inflow is incompatible with supersymmetry, or is incompatible with Dirac quantization, is incompatible with some other principle. And if that happens, if you cannot have your cake and eat it too, then the theory, when this happens, right? If you have an anomalous mode and you cannot cancel the anomaly somehow while preserving the other principles of the theory, then the theory is dead. It's inconsistent. It's in the swampland. Okay, so this is why the Cobartism conjecture is powerful, because it's talking about anomalies. Anomalies are purely IR effects that can study purely within low energy effective theory with the boundary. And so I can reliably put constraints on the theory like that. Okay, so that's the basic idea. And that's why I'm excited about this. I'm gonna be telling you now how to do this in some theory with 16 supercharges, blah, blah, blah. But that's just a proof of concept of the general idea. What I'm excited about is general idea. And in fact, I'm working on applying it to things like the standard model. Questions? I know it was like a bit abstract, like I didn't exactly tell you what the principles are. It will be clear in the example, but that's the basic idea. Okay. So
sorry, this anomaly can be cured by putting the system in a higher dimensional, I mean, as a boundary of a higher dimensional system, or not?
So that's the point. So the anomaly can always be canceled by putting it in a one-dimensional system as a boundary of. So, okay, but you cannot do it sometimes in a supersymmetric way. You cannot do it in a way that the UB theory would satisfy Dirac quantization. Okay. Good.
Yeah, absolutely.
Great. So we will use this point to get new constraints on theories with 16 supercharges, and we'll be doing very quantitative predictions here. So I guess that at the time where I say supersymmetry, a lot of people detune. It's like, I don't care about that. So why do we care about supersymmetry? Well, I don't care either. Right? I want to put constraints in the real world, model independent constraints, but this is a very difficult thing. And so by using supersymmetry, we have a technical tool which simplifies our life, while at the same time it still keeps many features of actual quantum gravity. Supersymmetric theories have perhaps weird spectra, like one fermion for each boson and so on, but they have gravitons, they have gauge fields, they have scalars. They're just like your average quantum field theory. And what I'm going to do is just not look at supersymmetry. I'm also going to look at supersymmetry in higher dimensions, because supersymmetry gets more powerful the more dimensions you have. Okay. By the way, I was told that it's okay if I go over time. Is that, I just want to double check that, because I probably am going to.
Yes, no, that's no problem. We've lots of questions, and it's good to hear the entire story. If people have to leave, then they can watch the record.
Good. Yeah, it's not going to be a lot anyway. Okay, so we have this simple problem, that it's understand this thing in higher dimensions with supersymmetry. Okay, so I want you to come with me to the arena of high dimensional supersymmetry, bearing in mind that we're doing only so as a proof of concept of this idea. Okay, good. So if I'm doing supersymmetry, I'm just gonna take a one slide introduction with supersymmetry. Well, it's just a fermionic extension of space and symmetry, where you have some fermionic generators that complement the Lorentz generators. And we like it because, I guess I told you that the whole point we're doing this is because it gives us a lot of control over all sorts of quantum effects and corrections, and makes things look classical in a sense. And just like any other symmetry, fields arrange themselves into multiplets called supermultiplets, and in this time, just the multiplets is mixed fields of different spin. Okay, so if you have just one supercharge, one multiplet of supercharges, because these things are wide fermions, you have 4 real supercharges. You can have more. You can have 8, 16, and the maximum, the most that you can have is 32 supercharges. If you have 32 supercharges, life is super simple. The more supercharges you have, the bigger the multiplets are. And with 32 supercharges, there is just one multiplet, the gravity multiplet. Okay, so when you have the gravity multiplet, you can write down all possible theories of gravity which have this supersymmetry algebra. And the thing is basically uniquely determined by supersymmetry. There's a little bit of freedom of ambiguity, but not too much. Okay, so in 11 dimensions, for instance, you have if you are doing this in 11 dimensions, which is the biggest dimension compatible with 32 supercharges, turns out that the answer is unique. There's just one supersymmetry algebra. And this produces some low energy effective field theory, some Lagrangian, which turns out to be the low energy limit of a consistent non-quantum theory of gravity, which is M theory. If you do it in 10 dimensions, now you have 2 different supersymmetry algebras with 32 supercharges. The corresponding theories at low energies are called type 2a and type 2b supergravities. And they are the low energy limits of type 2a and type 2b string theory. And with lower dimensions, basically what you get is compactifications of these guys. Okay, so this is a very simple setup in which supersymmetry all but determines the theory, but it already illustrates the principle, in some sense, the principle of string universality. There's the low energy supergravity theories that you determine purely from supersymmetry. And it could have been that some of these low energy theories just don't make sense non-perturbatively. It could be that they are not the low energy limit of a consistent string theory, but in fact, it happens that all of them do. So that leads to the idea that people call string universality, which is the idea that every consistent quantum gravity, at least if we have a lot of supersymmetry, is arising as the low energy limit of some effective string theory. Now, before anyone, I'm gonna stop a moment to take questions. I'm just gonna say that before anybody complains, I read this, calling this evidence for string universality is a long stretch. There's 2 supergravity theories in 10 dimensions, and the 2 of them happen to be low energy limits of string theory, that is not a lot of evidence. Okay, I'm gonna show you how we do better. But before I do that, any questions about this?
Just by M theory, you simply mean 11-dimensional supergravity?
Yes, I mean 11-dimensional supergravity. Yes, yes, good, right. So right, we have very strong evidence that this thing makes sense also non-perturbatively, coming from matrix models and all the web of string theory dualities. But it's true, yeah. Okay, so that's the idea. That's with 32 supercharges, life is boringly simple. So let's go to the next case. The next case you can do is 16 supercharges. That's, in fact, the minimal amount of supersymmetry you will have in more than 6 dimensions, which is the case I'll be focusing on. And just like with 30 supercharges before, life it's simple, but not as simple. There are 2 multiplets. There's the gravity multiplet, which includes gravity as a bosonic field. They also have fermions. I'm just listing the bosons. It includes the graviton, some gauge fields. And there's also the gauge or vector multiplet, which includes gauge fields and scalars, transforming in the adjoint representation of the gauge group generated by all the gauge fields. Okay. So there's 2 ingredients now. So 1 up. And but you will see the theories are much richer. Even though they're much richer, the Lorentz interaction, the Lorentz Lagrangian, is completely fixed by supersymmetry. And the only thing that you can do is to give vacuum expectation values to these scalars. These scalars are exactly massless. They parameterize what is called a moduli space. And you can give vevs to the scalars, whatever you want. That means going into the Coulomb branch of the theory. That's the jargon for it. And we even know what is the geometry and topology of the space parameterized by the scalars. We know everything about them. And you know, it's a boring theory. The interactions are completely fixed. The only thing that you can do is to give vevs to these scalars. Okay? Because the scalars are in the adjoint representation. The adjoint representation, when you give it a vev, you break the gauge group to a maximal torus, to U1 to U1 to some. In more general cases, U1 to some number R, which is the rank, plus the number of dimensions of the and that's what we say. That's the theory in the Coulomb branch. And the most that can happen is that at particular special points in the moduli space, you can have non-abelian gauge fields popping up. These U and Higgs partially with U1s. So if you want to fully specify a supergravity theory, it's fully specified just by the rank of the gauge group, the number, a simple number, the number of vector multiplets, and specifying what can happen at these special points in moduli space. And so the Swampland is just understanding which combinations of these can arise from low energy quantum gravity. Okay. So this is the question that I will be discussing now quickly. And let me start again with the case, with the highest dimensional case where you can have 16 supercharges. In 10 dimensions, the moduli space that I was describing collapses to a point, and there's basically only 4 possibilities, 4 possible gauge groups that are consistent with anomaly cancellation. These 2 and these other 2. These 4 possibilities were known since the 1980s. And since the 1980s, we knew that these 2 possibilities arise as the lower energy limit of certain string theories, periodic string theories. But until 2010, I mean, but these other 2 did not have any string embedding. And so there would be a counterexample to the idea of string universality. There's some supergravities that just don't have a string theory embedding. Except that in 2010, it was shown that these theories had a pathology. They're incompatible with supersymmetry once you take into account higher derivative corrections. So taking that into account, we get again this idea of string universality. Okay. The evidence is also not very strong. Now we get 2 out of 4, but you know, it's mounting. And the case I'm going to be describing is what happens when you lower dimension to 9, 8, and 7 dimensions. And I'm just going to be doing it at a generic pointer Coulomb branch, so the gauge group is U1. And the only date that I need to specify the theory is the landscape of possibilities is just a number, the rank of the theory, the number of vectors. I'm going to restrict to ranks lower than 26 minus the dimension because there are general arguments based on a different Swampland constraint, the Swampland distance conjecture, that the rank could not be bigger than this. But really, the arguments are going to be making are independent of this, and this is just a way for me to restrict to a finite set of possibilities. So if I restrict to a finite set of possibilities, that's how things look like. For 9, 8, and 7 dimensions, I want to know which possible values of the rank are there. So you see there's now many possibilities, okay? And we already know something about these possibilities, which I'm gonna let you know by color coding this, like this. So I've color coded this graph. Each square corresponds to a possible theory specified by a dimension and a value of the rank. Theories in red, we know already they're inconsistent because they have a global gravitational anomaly, as was shown by Albert and Witten in '82. Theories in yellow are the most interesting. They have no known inconsistencies, but there's no stringy construction for them either. So, if they are actually consistent, they would be counterexamples to the idea of string universality. And finally, theories in green have known string constructions. Okay. So what we want to understand is just we want to explain this pattern, and we want to turn yellow into red. Because if we turn yellow into red and we only leave at one dimension green and red, that means that the only possibilities that are consistent are the ones realized in string theory, are the ones that you get from string universality. So that's the basic idea. Questions about this, perhaps? Okay, long story short, we have a landscape of theories. We want to kill some. This is one slide telling you, what are the string compactifications that give you the known theories. You can compactify string theory in interesting things like the Klein bottle or the Mobius strip, and that's what gets you these theories. And so what I'm going to be doing, I'm going to be using the Cobartism Conjecture that I explained before to explain this modulo 8 periodicity in the rank. Okay, so I'm going to be showing that these possibilities 3, 5, 7, 11, 13, and 15 are inconsistent. And in 7 dimensions, we're not going to be able to kill all the yellow, but we're going to be able to kill half of it. Okay. So to do that, I need to tell you one more fact. I need to tell you a few facts and an assumption that I will be making about supergravity theories in 8 dimensions. The way I'm going to be using the Cobartism conjecture is by compactifying the 9 or 8 dimensional theories on manifolds which are non-orientable. And the reason why I can do this is because these 9D and 8D supergravity Lagrangians, they have a parity symmetry. And this parity symmetry is a particular kind. It squares to -1 on fermions. Okay, so parity symmetry squares to -1 on fermions. It provides an example of a pin- structure, which, by the way, of course, has also been discussed extensively in condensed matter literature. And this is, in fact, an exact symmetry of all known string compactifications. And it means that you can consistently put the theory on non-orientable manifolds. You can put the theory on manifolds on which the transition functions use elements that reverse parity. Okay, so those are 4 facts about the theory, and I'm just going to be assuming that those facts are actually true in every 7D, 8D, and 9D theory. They are certainly true at low energies. What I'm assuming is that they are not broken by some non-perturbative effects. Okay, that's the assumption. And what do I get out of this assumption? Well, as I told you, if it makes sense, the theory makes sense on pin- manifolds, you can compactify it on a particular pin- manifold, which is the real projected plane. Now, this is something that in string theory, right? You compactify means that you out of a d-dimensional theory, I produce a d-2 dimensional, which has a small copy of RP2 just floating around, right? And to this theory in 2 dimensions less, I'm going to apply the Cobartism conjecture, which tells me that the theory has a boundary. But that the theory has a boundary must mean something in the parent theory, because what the boundary is doing now is that this RP2 is collapsing to a point. Okay, so I'm constructing a boundary for RP2, and basically just about the only geometry that can be a boundary for RP2. It's this singular configuration R3 mod Z2. Okay, so this is what we call an orbifold. Has a singularity and has infinite curvature of the origin, kind of like a cone. Nevertheless, string theory often makes sense in things like this. And what we're saying is that because of these arguments, any quantum theory of gravity must make sense on orbifolds like this. Okay. And so if the theory makes sense on orbifolds like this, then you can just look at this thing and consider different string theory compactifications. By the way, this is of course true in string theory, and these objects we call them in general I-folds because it's short for inversion folds. And the point is that if you have these objects, you can make sense of the theory compactified on singular manifolds like this thing, T3 mod, like a 3 torus quotiented by Z2, that is like has 8 fixed points of this kind. And ordinarily you wouldn't consider it a valid background for compactification because of the curvatures, but because of this, you know now that it makes sense.
Sorry, I missed how you're thinking of this as a boundary, because I tend to think of a boundary as lower dimensional, but you've gone up in dimension.
Yes, exactly. So what I'm thinking is that, so I'm thinking of this RP2 here, right? And I'm compactifying the theory. So really I have RP2 times RD minus 2 floating around, right?
Yes.
Yeah, so what I'm saying is that lower dimensional theory has a boundary mode. And so I'm asking, what does it mean in terms of the higher dimensional theory that the lower dimensional theory has a boundary? Well, what must happen is that this geometry itself has a boundary, right? RP2 is being the boundary of whatever mode I have at the edge. And just about the only thing that can be the boundary of RP2 is R3 mod Z2.
Okay, so you're reversing it, yeah, okay.
Right, so that's the basic point, yes. Actually, yeah, the Cobartism conjecture makes a direct statement for all Cobartism classes without the need to compactify, but this is just a quick way to see how to relate with what I explained before.
Can I just ask something about pin minus?
Yes, please.
Unlike spin structures, pin minus and pin plus are not symmetrical. I think you can have pin minus in any parity of dimension, but not pin plus.
No, that's not right. You can have both pin plus and pin minus structures on any dimension, but it's true that a certain manifold, a particular manifold, may be sometimes pin plus and sometimes pin minus, either or both.
Yeah, but the Stiefel-Whitney restrictions are different. They're not symmetrical.
Yes, that's correct.
And you're in Riemann surface land here, so I guess it's okay for any genus Riemann surface. You're okay.
Yes.
Have you any intuition about why the pin minus and pin plus are different in their property?
From my point of view, you mean? From the point of view of theories? Yes. I was too quick about that. Sorry. So the reason is, again, supersymmetry. Okay, so the supersymmetry algebra in 9 dimensions and 8 dimensions is only consistent with a pin minus structure. So what you want, right? The supercharge is a Fermi. Okay, so it transforms as a spinor. And what you want for the theory to make sense in orientable manifolds is to specify how the supercharge transforms under reflections. Now, what happens is that in 8 dimensions and 9 dimensions, the supercharge transforms into a real representation. And another thing that is different between pin plus and pin minus is the representations of the Clifford algebra.
Which algebra? Sorry, what did you say? The transformations of what algebra?
Clifford algebra, the gamma matrix.
Oh yeah, right. Yeah, Clifford algebra. Yeah, sure. Yeah.
Yeah. So the only thing I'm saying is that in 9 and 8 dimensions, the only pin structure which admits a real representation is pin minus. And I know that is real because it's supercharges, which are real. So that's it.
Yeah, thanks.
Yeah. So I have these objects now, and now I can compactify on backgrounds with these objects. So for instance, I can consider a background which is a different compactification of the 9-dimensional theory, which is T3 mod Z2. And that produces a 6-dimensional theory. Now, in the 6-dimensional theory, I get fields by dimensional reduction, and they're going to be coming either from the fixed points from the twisted, what we call in string theory twisted sectors, the fixed points coming from these orbitals, and I have no idea what are the degrees of freedom living there, but I know there's 8 fixed points, so the 8 of them are going to produce the same set of fields, and those coming from the ball supergravity modes. So this would produce a 6-dimensional model, and 6-dimensional models, which are chiral, they have very strong anomaly cancellation conditions. This is a theory of gravity. Gravitational anomalies have to cancel. And that means that the number of fields in the theory, which is specified by the number of tensor multiplets, hypermultiplets, and vector multiplets, has to be equal in this way to 273. That's just a condition you need to satisfy. This is a problem that has been understood since the 90s. That's the only way the theory is consistent if you satisfy this equation.
In
So
6 dimensions.
Sorry?
In 6 dimensions.
In 6 dimensions. This is a very, very 6-dimensional thing on.
Okay.
So when you do that, well, you need to compute the numbers of these guys, and you can compute them explicitly. So supergravity fields, you can just do dimensional reduction. You get 1 tensor multiplet, 3 plus R hypermultiplets, and no vector multiplets. And you don't know what the fields at the singularities are, but you know there's 8 of them. Whatever they are, they contribute. It's a multiple of 8. So you take this, plug it into this equation, and you will find that this only works if the rank is 1 modulo 8. And well, just to flash you a slide that we know exactly how to construct these guys in string theory, and we know how to do it in every example, and when you can check with the precise numbers. In this case, I can actually tell you what is on the fixed twisted sectors. It all works beautifully. And so that's for the 9-dimensional story. In 8 dimensions, I compactify on the same thing, but now I get a 5-dimensional theory. Now, 5-dimensional theories don't have this powerful modulo 16 parity anomaly, but the same argument works, and using the modulo, they don't have the same powerful gradation anomaly as in 6 dimensions, but they have a modulo 16 parity anomaly. And taking this into account, using the modulo 16 parity anomaly, I get that the rank is 2 modulo 8. With one subtlety here, which we're not able to solve, there is a possibility that this parity anomaly is partially gapped by a TQFT. There could be a hidden TQFT, topological quantum field theory, that cancels the anomaly partially and would make our constraints weaker. We haven't been able to rule this possibility out, but we also talked to people. We couldn't find anyone who knows what that quantum field theory could be or how to construct it explicitly. So, you know, it could be there, might not be there.
Sorry, Miguel. Should be a sort of a Chern-Simon theory in 5D?
No, not really. No, yeah, it wouldn't do the trick. It's interesting. If you're talking about pin plus structures in 4 dimensions, then you can do something like this with indeed with modified versions of Chern-Simon theories. Sorry, in 3 dimensions. In 3 dimensions, but not in 5.
Not in 5. So
it just doesn't. Sorry, what?
Do you need a higher form, a B field, or a higher form to combine it?
Look, I honestly don't know. I just don't know. I don't know if the theory exists. That's my point.
Okay.
I'm just saying that it could be.
All right.
And in 7 dimensions, do the same argument, and you don't explain you get that the rank has to be 1 modulo 2. So putting all of this together, this is how the table looks like now. We explain the 1 modulo periodicity in 9 dimensions, and modulo this subtlety, we also explain it in 8 dimensions. And in 7 dimensions, we don't explain it fully, so there's some yellow still. But we have killed many possibilities. So all things considered, I think we can claim victory and say that we have achieved Coulomb branch string universality. String theory compactifications exactly match Swampland constraints. Bottom-up arguments from global symmetries produce some constraints, and string theory happens to exactly satisfy those constraints. And this is much more stronger evidence for this thing. Okay, so that's the basic result. I'm basically done. So there's just one more thing I tell you in 1 minute. Any more questions?
Is there a sort of periodic table behind what you're showing us? I mean, if we go down or not like
Pod periodicity or something like
yeah, pod periodicity or something like that. I don't know.
Good, good. Yeah, so let me tell you then a bit of story here. So the way that this is a problem, explaining this modulate periodicity has been an open problem for many years in string theory. And when you have coffee with people, you ask, how would you expect to solve this? The people that is like, oh, well, you're just going to compactify to 2 dimensions. There's going to be a string coupled to this. So the gravity multiplet has a B field, there's a string there. And often in 2 dimensions, we get the moduloid periodicities, which are related in the worksheet, which are related to things like pod periodicity and such. So that's where people thought the argument for this would come. And this is a very different argument. So it might be secretly related to that because, that other argument might still work after all in some way I'm not familiar with, but not that I know of. But yeah, certainly it's a good question. I wonder that myself. Yes. Okay, so it seems like all of the landscape of supergravity has been conquered by the Romans, but this is not true. There is a small village which holds out to the invaders.
Right.
And this is because, as I told you, I just understood what happens at generic points in moduli space, but at special points, you can have enhanced gauge symmetries. You can have non-abelian gauge fields. And so to fully claim victory, I need to tell you which, this is a table of all possible Lie algebras. I can tell you which Lie algebras can show up anywhere in moduli space and which ones cannot. So very quickly, this is the ones that arise in string compactifications. These are ones that have inconsistencies because of quantum anomalies. And there's these other 3 guys, G2 in 9 dimensions and symplectic groups in 9 dimensions, that nobody knows how to get in string theory. We tried very hard with these techniques, but we couldn't rule them out either. So that's an interesting open problem. And one thing that we could do, however, is to put constraints on the global form of the gauge group. So specifying the algebra is not enough. You need to also specify what is the global form. So like, if you have the algebra SUN, you can have SUN gauge group or SUN mod ZN. And so you can try and match which ones can exist. And the Cobartism Conjecture, these arguments can actually tell you, can put some constraints. So things in red should not be able to arise. And again, we checked. So basically, there's another group with similar arguments, got constraints on this from different arguments. We agree with them. And these guys, at the same time, more or less, that we put our paper out, had an amazing list listing all the possible forms of the global gauge group that can arise in string theory, in particular set of compactifications, which are heterotic compactifications. There's 340 groups. We checked all of them satisfy our constraints, which took some time. And then more recently, they are exploring a different class, the other class of string compactifications in 9 dimensions and 8 dimensions, where you can have these things, which haven't been explored before. So our table here was making a prediction. And we will have to wait for the results, but from communications with them, it seems like it's working out. So we're making a prediction here for global forms of the gauge group in string theory, purely from Swampland constraints, and it seems it's matched by what people find quote unquote experimentally. So I'm basically done. The basic idea is that you put gravity in boundaries, you can get a lot of mileage from that, and you can realize this thing very concretely in higher dimensional supersymmetric compactifications. You can explain Coulomb branch string universality and some features of the global structure of the gauge group. And of course, the things that we would like to do is to solve the remaining problems in higher dimensions, and of course, extend to situations with less supersymmetry. In particular, of course, we care about the standard model. So with that, I thank you all for your attention and stop right here.
Okay, thank you very much. There may still be questions, so the floor is open to further questions.
Miguel, so
yes,
it's very interesting. I'm not an expert in this area, but I understand some of what you said. But what really is the main driver? Is it that supersymmetry has to be used really extensively? I mean, supersymmetry is kind of an algebraic object rather than a differential geometric object, although there are links to differential geometry. And yet you used a topological comment between these boundaries. But really, I see mainly the supersymmetry is the main driver that if it was removed or perturbed, you wouldn't be able to do it. Is that?
Yes, yes. So let me elaborate on the precise way in which supersymmetry plays a role here, okay?
Yeah.
So, right, so there's an issue I glossed over. I constructed this R3, actually, sorry, I stopped sharing slides. I don't know why I was stupid. Right. So you see my slides, right?
Sure, yeah.
Mhm.
Yeah, so there was this thing, I was arguing for the existence of these objects.
Mhm.
And then I wanted to compactify them like this, right? But if you see, there's a point here where which I glossed over, which is a subtlety involving tadpole and cancel.
Yeah.
These objects can have charges under the 9-dimensional gauge groups. And so I need to specify what are their charge under the, the magnetic objects, right? So I need to know what their charges. And if for instance, if I need to figure out what are the charge quantization properties of this. Okay? The charge quantization properties you can study by studying the Dirac phase that you get when you get the charged particle moving around. The usual argument with the Dirac string, right?
Yeah, sure.
Only that this argument can be it's because now the angular geometry is not of the object is not a sphere, it's an RP2. There can be contributions from additional warp volume fields of the charged particle.
Yeah.
This is an effect that is understood also that happens in general orientable in string theory. And so warp volume fields can have a parity anomaly in this background and can contribute to the Dirac phase, can shift the charge condition. Okay, so that's something that can happen in general for objects with twisted angular geometry. And if you just don't say anything about that possibility, if you just consider the most general possibility, then these compactifications could be killed. It could be that it's impossible to cancel the tadpole for the compactification that I want to make. However, because of supersymmetry, I know that the warp volume theory of the electric particle under which I'm doing the Dirac quantization argument, I know that its warp volume fields, its set of ground states has to be supersymmetric. I know how many fermionic zero modes are there. And with this much supersymmetry, that's a multiple of 8, and that gets rid of the problem. So bottom line, that supersymmetry enters in kind of like a twisted way. It helps you determine the charge quantization of these guys. That's how it enters.
Okay, thanks, Miguel. Very interesting.
Thank you.
Any other question before I stop the recording? Well, let's thank Miguel again. That's great. Thanks.
Thank you. Thank you so much.